Okay, so remember we had a combination of the U's and now the V components that were happening in our power requirement for this pump. So now we're going to go back to this velocity triangle because we're trying to describe now these velocity components. So this was the W, right? Here's what you're trying to get at. And this is, let's say, U, right? So first thing is this V can be broken up into its components, right? Okay, so upwards you're going to have this R component, and there's the theta component, right? Because now this is going to, because I'm working in this system right here. Okay, so then this one here, since it's still perpendicular, this is actually going to be a U. Okay. All right. So let's talk about then how big is the velocity vector I care about to quantify energy. Well, that, just by definition of vectors, right, is the sum of the components squared. So if I square this, look at this. It's still a measure of size, so it's okay to square a vector magnitude because it's still telling you what's bigger and what's smaller. So the size of the vector I care about to quantify kinetic energy is the sum of the squares of its components, which are scalar values. Okay, so similarly for the W one, you're going to have, well, right, that's this, right? So I made another triangle this way, so that's still V squared. What have I done now, though? And so this time I have a U squared. I've done nothing but just look at a triangle and do Pythagorean's theorem, but still, sometimes these things are hard to see where they come from. Okay, so right before, what did we have? Right before we had this issue of right? We had this combination, a cross product of these two terms right here. So the idea is from using these vector quantities is I'm going to try to get this expression in terms of other expressions. And it's definitely doable because if you just look right here, if I square this and do out the algebra, you always get cross products of the two terms. So just by seeing that I could relate W in terms of a difference of these velocity components that I even cared about in the first place should kind of get, it's an aha moment because you're like, oh, once I care about that algebra, I'm going to get a cross product and I could actually figure out what that cross product of U and the V theta term would actually be. So that's kind of just the idea, right? So you just rearrange that. You take this equation and put it back in there. Okay, and then you get that V squared okay. And then what do you end up getting since you get a minus minus? It's in the notes. The idea is, okay, well, I'll do it. Boom. Boom. Plus, minus plus, so those cancel out. Okay. Then after that, I'm running out of room. Okay, so just right. Big reveal is this at any point you can write it as that. So this cross term that involved the torques and the power can be written in each individual velocity component involved in your pump. And that's kind of helpful for some, right? So that's just a way to to rationalize physically what's happening in pumps, because writing the cross term that way allows you to write out this kind of all-encompassing sort of specific shaft power. Okay, so this is somewhat useless, but you have to know it. The idea is this is 1/2 an absolute velocity minus an absolute velocity, right? So this right here is the idea. This is the actual increase. It's the actual increase in the kinetic energy from the pump rotating that happened to the fluid velocity. That's what that term is. Okay, in addition to that, we also will have the kinetic energy increase of just the fluid stuck to the impeller blade. Because again, remember, it's still turning, and because of no slip, there's still actually fluid just on that blade surface that's also rotating. So that's also an energy term that you should keep track of. If you ever look at your fan after you haven't cleaned it for a while, you'll see there's just a ton of dust on the impeller blades. So as that rotates, that has mass to it and still is rotating at this U. So that's still a kinetic term that you have to factor in. The only cool or whatever part of this thing is you've got a minus sign for this W, right? And this is a decrease So this is the decreased kinetic energy relative to blade coordinates. So this is the idea of it's a balance now of the absolute, right? You have the absolute fluid velocity, right? The fluid actually flipping around with it, and then also taking away the component of just this being relative to the blade. And a balance of all these things makes up the actual specific shaft power of your pump. All right. And again, the only only point of this, I think, is the idea that this U value is based on, right, this is involved in a W and an R, okay? And now these W's right here, those things had to do with the idea that if I just turn the pump off, right, I could shove fluid down that shaft and it would expand outward as well. So maybe you could understand already with pipe flow, right, these velocities are involved with, right, just like in the pipe flow stuff, right? So that's how I think of it, at least, of, these are just things I can calculate. And if I, since they're subtracting each other, you want to really see how big this term is, because you definitely don't want it to be too big or all just be negative, right? Which doesn't make sense. But that's just a way you can kind of rationalize what these terms are and their differences. But next, we're going to work towards actually, this is a rationalization equation based on like kind of whatever pump you would make, maybe even regardless of the geometry, you could still look at this equation and say, that's true for all turbo machineries. And you get an idea of what that would be. Or at least say yes, no questions, or that can't happen, or, oh, that term's way too big. So maybe remember it for that, because, you'll use it twice.